A breakthrough for scientists after they had a 20-minute conversation with a humpback whale.
There's a sound in the deep ocean that doesn't belong there. A rapid, clicking, mechanical, precise, repeating in patterns too complex to be random. For 100 years, biologists filed it under animal behavior and moved on. Then a cryptographer heard it for the first time and recognized it instantly. Not as whale noise, as a language, one that's been broadcasting beneath us for 30 million years, and nobody had ever tried to decode it. Here's what science thought it knew. Sperm whales click. They produce about 21 distinct patterns, short bursts called codas, and each one carries a simple, fixed meaning. A warning, a direction, a contact call. Researchers treated it the way you'd treat a traffic light. Red, yellow, green. A handful of states, no complexity, nothing worth investigating further. That consensus held for decades. Not because the evidence proved it, because nobody with the right ears ever questioned it. The crack started with an open door. David Gruber, marine biologist, Harvard's Radcliffe Institute, was sitting in his office with headphones on, reviewing whale recordings he'd collected while studying jellyfish in the Caribbean. The clicks were background noise. Familiar. Done. Shafi Goldwasser happened to be walking past. She stopped. Listened. Goldwasser wasn't a biologist. She was a cryptographer. Her career was built on cracking encrypted communication systems, the kind governments build to hide state secrets. She didn't hear animal sounds in that office. She heard ciphertext, a signal no one had ever run through a decoder. She looked at Gruber and said, "That sounds like Morse code. Have you tried running machine learning on it?" He hadn't. Nobody had. That question pulled in Michael Bronstein, an AI researcher who realized the same deep learning architecture behind large language models could be aimed at non-human communication. But they'd need data, not hundreds of recordings, thousands, with context attached to every single one. Not just what the whales said, but who they were saying it to, what every animal in the group was doing, and what was happening in the water around them. By 2020, the idea had a name: Project CETI, the Cetacean Translation Initiative. Backed by MIT, Harvard, UC Berkeley, 15 other institutions. They built a permanent research station in Dominica, right inside the migration corridor where sperm whale families have returned for generations. Biologger tags suctioned to whale skin, each carrying 3 synchronized microphones, GPS, depth sensors, accelerometers tracking body orientation to fractions of a degree. Everything that could give meaning to a sound, captured simultaneously. One of the voices they recorded belonged to a matriarch they'd been tracking for decades. Over 70 years old, born before military sonar existed. She'd been clicking to her family every single day of her life. They fed it all into the algorithm. Every recording, every voice, including hers. What came back demolished the science. The AI didn't find 21 codas. It found 156, but the number barely mattered. What mattered was what lived inside each one. Tempo shifts, rhythm changes, ornamentation clicks layered in repeating structural patterns. Those patterns weren't decoration. They were functional. They operated the way phonemes operate in human speech. Modular acoustic units combined according to rules to build meaning that no single unit carries alone. The whales weren't transmitting preset signals. They were constructing communication dynamically, from a modular phonetic system, the same architecture underneath every human language on Earth. And nobody in that room said a word for a very long time. A linguist at UC Berkeley, Gaspar Begus, took the research somewhere nobody expected. Instead of mapping coda patterns as sequences, he zoomed all the way in. Spectral imaging of individual clicks at the highest resolution modern phonetics equipment can achieve, microsecond by microsecond. What he found made his own field's assumptions collapse under their own weight. The whales were producing vowels. Not approximations, not acoustic coincidences. Controlled frequency modulations. The ah in father, the e in sea. And diphthongs, those gliding double vowel sounds like the oi in boy. Stop for a second. You and I didn't just wake up one morning making vowels. Our species spent millions of years evolving the machinery for them. A descended larynx, specific tongue muscles that exist for no other reason than shaping airflow. A resonance chamber sculpted across millennia for one single job, turning breath into speech. Same place through echolocation organs designed for hunting in total darkness, through clicks, under thousands of pounds of hydrostatic pressure, in an environment where light doesn't exist and sound is everything. Two species separated by hundreds of millions of years of independent evolution. Two completely different bodies, two completely different biological roads, arriving at the exact same destination. Biologists call it convergent evolution. Two unrelated lineages independently building the same complex trait because the problem they're solving demands it. And when the trait in question is vowel-based phonetic communication, something we assumed required human anatomy to even produce, the conclusion is hard to avoid. Vowels aren't a quirk of our throat. They're a feature of intelligence itself. Language, phonemes, combinatorial grammar. We told ourselves it was ours. It wasn't. Something else cracked it 30 million years before we existed, in the dark, a mile underwater, and it's still running. But knowing they have the alphabet is one thing. What the team found next is that these whales don't just possess the building blocks, they use them on each other, deliberately, in conversation. Shane Garrow has spent 13 years with sperm whale families off the coast of Dominica, not observing from a research vessel, living alongside them, watching them raise their young, coordinate hunts, and talk. What he describes doesn't sound like animal behavior, it sounds like family. He's watched a mother nudge her calf toward another adult, handing a child to a babysitter, then exchange a short burst of clicks before diving a mile down to feed. A few parting words. He's seen a calf press its head against its mother's jaw and hold there, clicking softly, for minutes. No urgency, no function anyone can identify, just contact. He's recorded exchanges lasting over an hour, multiple whales clicking over each other, responding, building on what the last one said. There's turn-taking, there's rhythm. And sometimes, two whales click at the same time, interrupting, which Garrow says seems to be perfectly fine among close family members, the way it is among ours. Now, think about what that demands from a brain. Selecting the right coda for the right whale in the right moment. Adjusting what you say based on whether you're addressing your calf or your matriarch. Modifying your response based on what the other whale just communicated. That is not stimulus and response. That is pragmatic language use. And it requires something we used to believe only humans had. A theory of mind. The understanding that the whale across from you holds a different perspective, and that your communication should be shaped to reach them specifically. Dominant voices and quiet ones. Exchanges that look like disagreements. Others that feel like reassurance. Private clicks shared between specific pairs, and calls that seem to address the whole family. All sustained by the largest brain on Earth, 6 times the mass of ours, loaded with neocortex and spindle cells, the same structures that govern emotion, memory, and language in humans. That matriarch off Dominica, the one whose voice has been running through the algorithm since the beginning, she's been having these conversations every day for 70 years. Clicking to her daughters, adjusting her tone for her granddaughters, passing something down that nobody on the surface can translate yet. Last year, the team noticed something in her recordings. The pauses between her codas were getting longer. Her click sequences were louder. She was repeating herself more often. She was shouting. Because here's what's happening to them right now. Commercial shipping lanes run directly through their acoustic habitat. Military sonar floods frequencies that overlap with the bands these families use to speak. Industrial noise saturates every ocean basin on the planet. And in water, sound doesn't fade. It carries for hundreds of miles, with nowhere to go. We're not causing noise pollution. That phrase is too clean for what this is. We are jamming the communication network of a culture older than our entire species. Every mother calling to her calf through a wall of engine drone. Every matriarch's warning swallowed by sonar. Every piece of knowledge passed from grandmother to granddaughter for centuries, drowned out. If they speak, and the evidence says they do, we've been screaming over them for 100 years. And we didn't know they were talking. The AI has mapped the grammar, cataloged the vowels, profiled individual voices by acoustic fingerprint, tracked family conversations across years of recordings. The architecture is real, peer-reviewed, published. What no one knows yet is what any of it means. Structure isn't meaning, not yet. Project CETI is now correlating specific coda sequences with observable behaviors, matching what was said to what was physically happening at that exact moment. Next-generation biologger tags feed synchronized data into a behavioral archive, cross-referenced against decades of observation. They're building the dictionary, one word at a time. And that matriarch off Dominica, the one they've been recording since the beginning, she's still there, still diving, still clicking to her daughters in a language we only just admitted was a language. She remembers an ocean before sonar. She's watched the water warm, the prey thin out, the noise press in from every direction. She has communicated something about all of it to her daughters, her granddaughters, the calves she helped raise, every single day, for 70 years. And every word of it happened in a system we couldn't read. The alphabet's been found, the decoder's running. Somewhere in the growing archive, buried inside thousands of hours of recordings, the first translatable sentence is waiting. We're not there yet, but the gap is closing. Here's what keeps the researchers awake. It's not the question of what she's been saying to her family. It's the possibility that at some point, she said something about us, and we'll have to sit there and read it. If a species has its own language, its own culture, and a documented theory of mind, do they deserve legal personhood? Or do we keep looking the other way? Type personhood or looking away in the comments. And if you enjoyed watching the video, hit the like button and subscribe to Hidden Latitude. The day Project CETI decodes the first full sentence, you'll want to hear it the moment it surfaces.